So, nitrogen cycle. We kept saying nitrate, 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 right, as the nutrient. There is so much nitrogen in the atmosphere, 70%, but in the ocean, nitrogen is actually a limiting nutrient. Okay, so where does most of the nitrate come from? There is obviously some running in with the rivers, but they come into the coasts. In the vast, wide open ocean, from getting to the coast to the middle is going to take a long time. Nonetheless, it happens. There is so-called nitrogen fixation by lightning. Lightning oxidizes nitrogen and forms what is called fixed nitrogen, or forms of nitrate that are usable by photosynthesizers. Okay? But most of the nitrate in the ocean is produced by so-called nitrogen fixers. I mentioned this before, diazotrophs they're called, trichodesmium and so on, which have the special ability to take dissolved nitrogen in the water and use nitrogenase, an enzyme which is also there in plants, and produce nitrate. That nitrate is then used by other phytoplankton. And I had mentioned this in the context of what would happen in global warming. So if global warming makes the surface warmer and increases the stratification and makes it harder for mixing nutrients from below, remember nutrients increase with depth, nutrients from below into the euphoric zone, then potentially the nitrogen fixers have an advantage, because if there is enough phosphorus, they can do their job and use nitrogen and compete better in nitrate limited waters. That's where phosphorus becomes critical, because nitrogen fixers actually need phosphorus. Okay, so nitrogen fixers provide some flux of, they have a reservoir as nitrogen in the atmosphere, and they fix nitrogen into the surface ocean, which provides a nice pool of fixed nitrogen, which is oxidized nitrogen, not N2O. N2O is a greenhouse gas which is not used by biology. Ammonium and nitrate. Nitrate is converted to ammonium, and in fact, even when photosynthesizers use nitrate, they actually convert it to ammonium and so on. So details, nonetheless, there is that flux. There is a downwelling of nitrate from the surface, as always, biological pump, right? Photosynthesis uses it, sinks, dies, eaten and spit out fecal pellets, etc. That's a biological pump, right? So you have direct biological pump and convergence and downwelling. So there is a fixed nitrogen in the deep ocean, which is greater than the fixed nitrogen in the surface. As we know, nitrogen increases with depth. But there is also denitrification. What is that? So there are other bacteria that live in the ocean, or also in the soil, away from the surface where there is no oxygen. They want oxygen. How do they get oxygen? They take nitrate and nitrite, NO3 and NO2, and they produce oxygen by splitting it. They are called denitrifiers. Okay, so denitrification ends up converting the fixed nitrogen back into dinitrogen, or N2. Okay, that's the loss term. So there is a N2 fixation, which is a source term. Denitrification is a loss term, and we'll see that there is a big relation between nitrogen and phosphorus and oxygen poor waters and so on and so forth, because in the oxygen poor waters, if you want to live, you can produce your own oxygen with this method, and if you can, you compete better than those who cannot produce their own oxygen, right? So there is nitrogen burial in the sediment. There are nitrogens in sedimentary rocks, which is not a small amount, and there is a weathering of that when it gets exposed, and there is nitrogen fixing on land as well. Nitrogen fixing in forests, soils is a big term. There are bacteria which do that as well. Okay, so there is nitrogen fixation on land as well. And there is denitrification on land as well, because things that live deeper in the soil where there is not much oxygen, they denitrify. So this is the nitrogen cycle. So how are they coupled? River inputs phosphorus into the water. Nitrogen and phosphorus ratio becomes very critical. So input increases, then the nitrogen to phosphorus ratio decreases. So this coupling is negative because phosphorus is in the denominator. If you increase phosphorus, you're going to decrease the nitrogen to phosphorus ratio. Remember, nitrogen is coming mainly from the atmosphere fixed by diazotrophs, whereas phosphorus is mostly coming from the rivers. There is no big flux of phosphorus because there is no phosphorus in the atmosphere. Okay, so the coupling between nitrogen phosphorus ratio to rate of nitrogen fixation is also negative, because if nitrogen to phosphorus increases, rate of nitrogen fixation goes down. Okay, so if there is more nitrogen, then they don't need to fix as much. You can think of it that way. And if rate of nitrogen fixation goes up, then obviously nitrogen goes up, so nitrogen to phosphorus ratio goes up. So there is a negative feedback loop in the ocean. This is an external coupling, so we have to worry about what happens in the ocean. So there is a stabilizing feedback between nitrogen and phosphorus. So in this sense, phosphorus becomes the ultimate limiter, because unless nitrogen fixers are producing fixed nitrogen, there is not enough photosynthesis and production, but they cannot fix enough nitrogen unless there is phosphorus coming in. So phosphorus is considered the ultimate limitation. So here is nitrogen fixation in the upper 100 meters. You can see where the locations are, and you can see that low N to P is also the region where there is denitrification happening. Okay, so high N to P, not much denitrification. Okay, low N to P, low N to P, low N to P, there is lots of denitrification. So you can see how there is a very strong coupling between primary production, because nitrogen is a nutrient, and denitrification related to production, because there are heterotrophs which produce oxygen by splitting nitrogen, and nitrogen is fixed by nitrogen fixing bacteria in the ocean as well. So carbon cycle and phosphorus cycle, nitrogen cycle are all related, and very closely related in fact, and there are feedbacks at short-term and long time scales that are needed for maintaining equilibrium. The question is, how are we changing the equilibrium? How are we changing the time scales of equilibrium, and who pays a price for that? That's the critical thing to look at. So we've been looking at fish and so on with various pressures, but we also have to worry about the nitrogen cycle. It turns out that nitrogen cycle on land is massively perturbed by human activities because of fertilizer use. Nitrate is a huge ingredient in fertilizers, which is used very heavily in agriculture. Remember the Haber-Bosch process, for which they won the Nobel Prize. I think one of them did. It was the first industrial large-scale production of ammonium which changed the game for agriculture. It made agricultural productivity very feasible, large-scale increases in yields possible. But nitrate also got used in bombs. So maybe more people got killed by bombs than blah blah blah. But anyway, some good things come with some bad things, but we do the bad things, right? We don't have to, but that's the way we are.